to be here. Thank you. And thanks for coming in on a Saturday morning. It's an honor to be here. I'm going to be presenting work done by my whole company, lots of colleagues, and I'm really grateful for them. I'm hoping that in this talk this morning, everybody will get some nugget of something useful depending on your background. In particular, I'll be talking about a little bit more on the technology that Alex talked about, some of the core stuff, as well as how we go out and operationally use these systems to collect data. And hopefully by the end, you'll get a sense of the answer to some of the questions of like what's possible today. So just the roadmap, we'll start with talking about a little bit of a pitch from my company, just one or two charts of what's actually available for forestry today. Then look at multi-look collections. So we talk about angular diversity, seeing a point on the ground from many different view angles, and I'll talk a little bit more about how and why that's important and how we do it effectively and efficiently. Then I'll talk a little bit about why single photon detection is particularly adapted to forestry, and one of the reasons is the high sensitivity. Going to space is absolutely interesting and important in a lot of applications, but even if you're just flying at normal aircraft altitudes, it turns out that the Geiger-mode approach gives you things that other approaches just don't. I'll walk you through a couple of examples and then talk about really fast, efficient collections at scale. How do we take all this great stuff and make it work at scale? So just jumping in right there. Just a quick summary of the company to give you a sense of scale and so on. We are, as you've heard, a spin-off from MIT Lincoln Laboratory, and what in particular we're spinning out is systems, so putting together components from other folks into systems, making those work effectively and easily for customers, and all the processing that you have to do to convert all those raw photon to digital conversions that Alex was talking about. How do we convert those into nice clean point clouds? One thing that's different from other entities that have done in the past Geiger-mode Lidar work in a commercial way, our scanning is very agile, and that turns out to be extremely important in forestry applications. And then the area collection rates, of course. You can read the rest. We do sell systems, that's our primary business, but we're also very happy to do pilot projects for customers and work with people who might want to use these on a wider scale. This is an example of a system we recently developed and provided to the New South Wales Rural Fire Service. Let's see, I want to get my pointer working here. Pointer options, laser, there we go. So they have installed this black box, and it is literally a black box that's strapped on the bottom of one of their airplanes. It's on a King Air 350. That's this system here. Here's a few specs on it. It's a 50-watt laser, so it's pretty hefty. They fly 8 to 15,000 feet. The data rate coming in is around 260 million detected photons per second, and at this altitude of around 8 or 9,000 feet above ground. So you can think about the data rate that allows you to get is pretty. It allows these things to work at scale. We have another system that we've recently delivered for another customer. This is kind of bigger and better, 100-watt laser, it's bigger aperture, higher data rates from much higher altitudes. So we try to make what customers need. And here's a table. Don't bother looking at the whole table. Maybe we can focus just on the center column here. We have small, medium, and large, you might think of it. But think about an application where maybe I'm just doing wide area mapping in an unobscured area, not forestry. We're talking about area collection rates of 1,000 square kilometers per hour. These are just regular commercial manned aircraft. That's kind of what we do. Typically, we like to have our systems point to the side a little bit. It gives us the ability to see the side of a building, the side of a tree, and the downside is that you kind of need to turn around and come back and go the other way to get the other side of everything, but you'll hear more about that. Anyway, let's move along. So multi-look collections are really important. I'm going to show you a little video of how we do our scanning to help you understand kind of how this works. Like any LiDAR system out there, we have a laser beam that we shoot down to the ground. Think of it as maybe a flashlight in our case, and Alex walked us through this too. In this case, it's illuminating the footprint of a camera down on the ground. So we typically have 32 by 128 or 256 pixels here. And that combination of a flashlight and a camera, we can sweep around however we want. That's kind of arbitrary, and that's to be engineered by the people doing the data collection. In fact, we can point it anywhere within about a 40 by 40 degree, what we call the field of regard of the sensor, the area that it can look in if so desired. So when we go to do a mapping project, for example, we'll typically break it into these little polygons, and as we fly along, we repeatedly scan each one. And if you kind of put your eye on maybe one polygon, it gets interrogated multiple times as we fly along. As long as it's within the field of regard, we can keep revisiting it. And the advantage is we get these multi-angles. Typically for like a 1 kilometer wide swath that we might be collecting, we might get 4, 5, or 6 different view angles on a pass. Typically, as I said, we like to turn around, we come back the other way and look at the other side of everything. But we really like to be able to get in all those little nooks and crannies between the buildings, or alternatively in a forest to see through all the little openings in the canopy. If the aircraft kind of wiggles around, that's okay. We put in the coordinates on the ground that we want to scan for each of these polygons, so we do a correction for roll and pitch variations. Those boxes don't have to be the same size. They can be different sizes. They can be aligned differently. You can have multiple ones, kind of however you want. So one piece of hardware gives you a lot of flexibility in how you might go collect. So what I just showed you here was a string of boxes like this. You don't have to have them in a straight line, as you sort of saw in that movie. You could also do a corridor map where maybe you lay out your boxes to follow a meandering road or a power line or a pipeline or whatever. You can set the width and the spacing and the location of those to match what you need. You could also go scan, and Alex showed some of this, a single target. Maybe it's a circle, it's a square, it's a weird shape, whatever you want. And as you fly over it, you can poke at it as many times as possible. You might get 10 to 20 different views of it on a single flight line. And if one is good, maybe hundreds are better. And this audience, and I'm trying to get people to think about this to see if maybe it's interesting. I don't know if it is. But what if we put down an array of these smaller targets? Maybe these are half a hectare or something like that, and they're spread out across a large area. And at least on one collect, we go through and we get really high density data on all of these little reference points, and then you kind of do sparse sampling. Maybe you follow it up with a wide area map that's synoptic and gets everything. I'd love to hear your thoughts on that. All right, so here's some actual data to show a little bit more of how this works. This is just a small little area that we scanned a much larger part. This is a small section of a bigger area. And this is the raw data. So each of those dots corresponds to one of those detected photons. So there is noise in there because there's background light and so on. There's also shadows because it was collected from just one angle coming down. So big shadows, and on these power lines here, you can sort of think that maybe there's something there, but it's not really obvious what that is. I can now collect from multiple viewpoints, as I talked about before, and you can see the shadows are kind of shifted around. Well, that makes sense, when you move your head, right, you see shadows move. But also you see that in some of these wires are pretty bright, and in some, maybe over here, the wires are pretty dark. And it kind of depends on how shiny surfaces are and the angle from which you hit them. So the next step then is to put all these pieces together. We call that aggregation. Oh, nothing major there. And we get an image like this. And what's different now is we have filled in those shadows substantially because we pick, wherever we got signal from any one of these scans. And there might be more than 4 scans here, I forget. Also, we can see that these wires show up much better. We start to integrate up some signal to noise there. You see a lot of complexity of the canopy architecture, and we've reduced the noise. So over here you can see, or maybe you can't in that view, I don't know, but there's some, on my screen I see a little bit of background noise, and we're able to turn that off by only displaying the points where we had a high confidence that it was a real surface. All right, I've been coming at you pretty hard for a little while, but I think that's a really nice summary of kind of how this all works. All right, so that was one thing. This was the multi-look collection. It's really important to look at scenes from multiple viewpoints. But the other thing is about the single photon sensitivity. And this is a little bit of a point for the experts in the room, but you're all smart, we'll figure it out. What I'd like to walk you through is a little bit of a simulation of how we would look down through the canopy. And here I'm not doing any of that multi-angle stuff. I'm just taking I've specialized down to one column of light as in the airplane is in one spot looking down through a tree. So how does this work? So think about lots of different branches at different heights in that tree intersecting that column of light. And these lollipops here are supposed to represent in some sort of a cartoon way the amount of intersection of each of those branches coming in from different places into that kind of column of light. So two things happen. One is it obscures the light from going down further. So you can see the width of the little thing here coming down. That's the amount of light that made it past that obscuration. And then there's also the reflectivity, which is the amount of light coming back. Okay, so I have each of these coming down. And the ground down here may not have a high reflectivity, but no light goes beyond it. So that's what I'm trying to show. Okay, so our job as a LiDAR system is to poke down, shoot laser pulses down through here repeatedly and see what we can find. So in this particular simulation, I'm putting down 2,000 laser pulses and I'm rolling the dice. And in this particular dice rolling exercise, the blue is telling us how many photo detections we got at each point vertically. So you can kind of think of a data structure in which I have a vertical chimney and I've distributed it up into these 3D chunks at each level, and I'm just simply counting up the number of detections that I got that were in that voxel, you might say. Now, of course, in the real world, we don't have those nice black curves to tell us what's supposed to be there. All we have is the blue. And so our job is to somehow or other get rid of the noise and to find peaks, even when maybe there's multiple peaks that are close together. And then we will, at the middle of the peak, and middle is in quotes because you can be very sophisticated about how you do these things, I'm going to put a dot in my output data structure and say there's a real surface in that XYZ point. So in this example, I might put a dot here, 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 maybe here, here, and here. Okay, and I don't want to put a dot down here. So a very simple-minded way to answer these questions: where are the surfaces, how reflective are they, and more importantly, how confident can I be? A simple-minded way might be to use our intuition of real surfaces are clumps, whereas noise is kind of uneven, or it's evenly distributed more or less. And that's a few thoughts on noise. But anyway, a simple way that we might do this is to just set a threshold. And we can adjust where to put that threshold. And as I go higher, well, let me ask you all, if I put the threshold higher, what does that tell me about my confidence? Lower confidence. I'm going to say it's higher confidence. If I put the threshold higher, I have to have more signal. Maybe that's what you meant to say. It's more signal, so I have higher confidence that there's a real surface there. Whereas if I put it lower, that's lower confidence that I have a real surface. So in fact, what we typically do is in our data products that we provide to customers, we attach basically a peak height onto our points, so that in your data viewer, you can dial up the level of confidence that you want and say, like, I don't want to look at things that may or may not be there and it might be noise. I'm going to just turn those off. And I get the big picture, and then I zoom in on like those power lines. I say, how many lines were there actually? Then I dial my confidence back down. I say, I'm willing to look at some noise points in here, and I get to see lots of structure. And your eye sort of does, or your brain does some pretty amazing signal processing and looks at long linear features or whatever, branches or whatever. All right, so back to the thing about sensitivity. So what's going on here is I've collected 1,000 to 10,000 laser pulses going down through my canopy, and I'm able to find very, very weak returns. We're talking about 5 to 10 detected photons over the course of maybe thousands and thousands of laser pulses. In more traditional LiDAR systems, like your Regals and that sort of thing, the technology they're based on, they have a light pulse that comes in and it triggers a photodetector, and in their electronics, very sophisticated electronics, but effectively there's some electronics that have a thresholding built right in. And on one laser pulse, you have to get up above the noise in order to say that's a real point. This is different because on one laser pulse, our signals are very, very low, but we aggregate them together from all the different viewpoints and everything, and at the end of the day, then we go and after we've aggregated and say, does this exceed the threshold? So it's kind of a different way of doing it, and it allows us to detect these very weak signals, either from small branches or from very weakly reflected ground. All right, so that was that one. Just qualitatively looking at it, this is 4 different scans put together. So this is the raw data. So I have each of these little dots as a time that one of these detectors fired. We're looking in from 4 different angles at this piece of ground down here. If I zoom in on that, then you can see, yeah, actually most of the returns that I got are from the real scene, and there's a little bit of volume noise up here, but kind of just with your eye, you can say, oh yeah, you'll be able to go in and find where those surfaces are. All right, so let's put that all together and go look at some real data from a small patch of forest. In this particular example, this was at the University of Idaho experimental forest. And the data I'm going to show you was from not in the opening, but up under the trees. We were able to somehow get a full tenured professor to go up and take these pictures for us. Thank you, Mark. And you can ask me more about the site later. I believe it was on quite a slope.
Yeah, it was a steep slope. Yeah.
Steep slope, good, okay. More specifically, this was a pretty small target because this was kind of an R&D type of collect in this particular example. 150 meter area, so pretty small. We collected it on 4 passes, and each of these dots is intended to show you the location of the airplane as we flew past. So here I think we were flying eastbound, and then we did northbound, westbound, and southbound. And on each one of those, we're looking to the left. This is the area we were looking at. These are degrees off of vertical, and so the airplane kind of flew by, and so you get the picture. So at the end of the day, we had 64 scans, which is way more than any normal person would take, but we wanted to be able to down select and do experiments in the processing to figure out, make curves, right, that saturate and all that sort of thing. All right, so the next step is to find the bare earth. We said it's a very steep slope, so for our analysis, we want to find out where the ground is everywhere. And there was a whole paper that one of my colleagues, Jacob Lawrence, put together. I'm kind of plagiarizing his results here, but it's all in the company, so it's okay. Anyway, once we've found where the ground is, then we can attach height above ground to each point. You're all very familiar with that. And of course, to digitally defoliate, we just don't show all of those points. We just show these down here. And I believe this was 2 meters above the ground to slightly below the ground. And you see a lot of debris on the ground. These are downed trees and so on. So let's zoom in just on this little section. And it looks like there's some trees kind of laying on top of each other. There's some bushes, smaller things. There's some stumps here and so on. It's a lot of fun to look at this data. Here's a couple of pictures of that area. This is looking up from about right here somewhere. And lo and behold, look, I've got this tree, which is this one. I've got this guy laying down here underneath of both of those, and I can see that's underneath of those. I've got this guy sticking up over here, that's this one here, and this little skinny fellow is right across here. And we're looking forward to getting these point clouds analyzed in depth for actual measurements and the accuracy thereof. All right, another question you might ask is, well, you took 64 scans, so you really need all those seriously. Like, the more you take, the more it costs, basically, to the questions of cost. So it all depends, right? What's the question you're trying to answer with this data? So in this example on the left, we randomly selected 5 of those 64 scans. We aggregated them together, and we processed it at some resolution. I think it was maybe 20 centimeters or so. And you see there's a lot of voids. Well, you might sort of expect that because the trees are reasonably dense. But for certain questions that you're trying to answer, maybe this is perfectly good. On the other hand, if you really want to see the structure of the vegetation down here, right near the ground, then you need more scans, and in this case it was 25. All right, so can we do this at scale? And obviously the answer is yes, or I wouldn't be wasting your time here today. But let's take an example with our Vulcan system, and let's say that we wanted to get 25 points per square meter under the canopy on the ground. And let's just, for example, say that I'm going to do that by 16x oversampling. And by oversampling, what I mean is, and I'm going to go back and chart. On this one, we did 25 scans, so that's basically 25 times the data density we would have expected if we were just out mapping in general unobscured surface. So that's 25x oversampling. This is 5. I'm going to go forward a couple charts. So in this particular example, just to put some numbers to things, let's say 16x. I said we can do 4 scans per pass as we were just flying straight down the line. So maybe we have 4 passes, maybe arranged like this, forward, backward, and then 50% swath offset. You're all used to that sort of terminology. And in this case, around 130 square kilometers per hour is what we're talking about, even when we do for those 4 passes. And this is the spatial resolution that we're talking about. That's one particular point in a wide parameter space that you might use. So, you know, 1 point is good, thousands are better. So here's a plot to show you the area collection rate, square kilometers per hour, that we could go out and get as a function of the aircraft altitude, because there's trade-offs that you want to make with altitude. And let's focus just on the green line for now. If on each pass, I'm engineering my collection parameters so that I get about 100 points per square meter on each pass. Maybe that's 25 points per square meter times 4, because I'm doing 4 scans, okay? So a total of 100. Then I'm on this green line here, and you can see that at 8.5 kilofeet, we're around, let's see, this is 100, 200, 300, 400, 550 square kilometers per hour for each pass. That's my area collection rate. That basically tells me the width of my scan on the ground that I would take. And in this example, I believe that comes out to around 800 or 900 meter swaths that we would be taking. And then we fly them twice, and we do 50%. So, again, it really depends on the question you're trying to answer with the data, but these systems that are commercially available out there allow you to engineer the collect to match the exploitation that you're trying to do, whether it's forestry or military or surveillance or whatever. All right, deep breath. So we've covered a lot of ground. Just to summarize it all, these systems are available for commercial use, and we're super excited about that. I mean, I started the company to do it, so clearly I'm excited. Hopefully you are too. We talked a little bit about aggregating data together from many laser pulses as well as many scan angles to mitigate shadows and to use that sensitivity. We can tune our confidence thresholds to either really totally eliminate all the noise or dial it back and be able to see weak signals at the expense of seeing a little bit of noise. It's a nice knob to be able to turn. The kind of scanning that we do, we call agile georeference scanning. It's a patent pending thing because we tweaked it just a little bit from Lincoln Lab, just enough to get a patent. But anyway, it does allow us to engineer our collections, and I think that foliage penetration really is one of the key applications of Geiger-mode, at least unless you want to go to space. So with that, I'll show you a nice picture from the University of Idaho, and any questions at this time.